And each connection between the neurons in the preceding layer and the neuron in the current layer has a weight value. For example, let's see the first neuron at the second layer highlighted in green. This neuron, N21, is associated to 3 weight 1 and weight 2 and weight 3. Likewise, the second neurons N22 is also associated to 3 different weights, weight 4, weight 5, and weight 6. And using these weight values, we can simply obtain the output value of each neurons by calculating the sum of weighted inputs like highlighted in the blue equations. Likewise, we can obtain the output value of the second neurons at the second layers. And the output of the layer consists of the output values of neurons in the layers. For example, the output of the second layer is a vector of 4 output values of neuron from V21 to V24 in the second layers. And using the output of the second layer and their corresponding weight, we can the next layer's outputs. Again, using the third layers of output values, we can finally obtain the output layer's value. And an activation function is one of the key components of DNN as well. At a really high level, the job of activation function is to use for achieving the better performance of DNNs. For example, this fully connected neural network takes on images and aims to correctly classify whether this image is dog or cat. And if the image data set spread like right side, this neural network can learn how to classify data by using a separable orange lines. So for this easy to learn data set, we don't actually need an activation function. But what if image data set is more complicated before? Then using a linear line is not so easy for classifying data set. In this case, if using the nonlinear activation function at each layer, your network is able to classify this non-trivial data with these quadratic curves. And there exist diverse activation functions like sigmoid, LELU, arctant, and so on. And let's look at a simple but quite effective activation function, LELU, which is rectified linear unit. This function takes the output value of each neurons and simply returns the larger of 0 and the output values. So suppose that the output of the second layer V2 is like that. Then this nonlinear function returns these output vector output values, and usually we say that the first and the third neurons with the output values greater than 0 are activated, while the second and the fourth ones are inactivated. And okay, so far we learned basic terms in DNNs. So finally, let's see what neuron coverage means. Neuron coverage is the first coverage metric presented by Deep Explorer paper for testing DNNs. So it is really intuitive metric and can be easily calculated. And to calculate the neuron coverage, we should know the meaning of the activated neurons in this works. The neuron is activated when its output value is greater than a certain threshold zeta. For example, suppose that a DNN having 10 neurons from N1 to N10 in total is given, and their output values of the 10 neurons are from V1 to V10. And suppose that the certain threshold is set to 0.5. And when taking input factor I1 as input, and suppose that the output values are calculated as follows, then the number of activated neurons in this case are 5. Because the 5 output values of the neurons are bigger than the threshold 0.5. And so the number of activated neurons are 5, and the neuron coverage is calculated by dividing the number of activated neurons into the total number of neurons. So in this case, the neuron coverage will be 15%. When taking another input factor I2 as input, other neurons can be activated as follows in this time. So as there are 3 activated neurons, so neuron coverage will be 13%. When using these 2 input vectors sequentially, the accumulated neuron coverage will be 70%. And the Deep Explore paper argued that increasing neuron coverage will lead to find many incorrect corner case behaviors of DNNs. The experiment results support their claim as well. For example, Deep Explore tried to change the original input 1 on the left into the input 2, which is direct version of input 1, toward improving neuron coverages. As a result, this changed image caused NVIDIA Dave to self-driving car platform to guide the driving in the wrong directions, actually. Okay, I will introduce one more simple coverage metric presented by Deep Gauge papers. This paper has presented diverse coverage metrics from the neuron level coverages to the layer level coverage metrics. And among them, top K neuron coverage is the layer level coverage metrics. So this technique is similar to neuron coverage, but also consider each layer characteristic. So to calculate the coverage metric TK and C, we first collect the K neurons with the highest output values in each layers. Like neuron coverage, suppose that the DNN takes an input vectors, I2 in this case, and calculate the output values of each neurons as follows. Then suppose that the top K value is 2. We collect the 2 neurons with the highest output values in each layer and mark them as activated neurons. So for example, at the second layer L2, the first and the first neurons are considered as activated neurons. And unlike neuron coverage, the TK and C does not have specific threshold zeta. Instead, this metric aims to activate K neurons, which are relatively high in each layer in various ways. Okay, so let's sum up the goal of DNN testing. So the goal of the DNN testing is to generate inputs that are likely to increase diverse metrics for testing DNNs and find some adversarial inputs that trigger the incorrect behaviors of the DNNs. Okay, finally, we can discuss about this lecture's title, White Box Testing of DNNs. Like the general goal of testing DNNs, the white box testing method also aims to generate the input vectors that are likely to increase a given matrix. So this technique takes a deep neural network model like Rectified and a set of inputs to mutate as input. And then it generates the mutated input that effectively increase a given metric such as neuron coverage in the limited time budget. And to achieve this, the key idea of the white box testing method is to use the gradient of the selected internal neurons. And I will explain an example for explaining the intuition of this key idea. When a given metric is neuron coverages, to maximize the number of activated neurons, we should focus on increasing the output values of the inactivated neurons. So suppose that DNNs takes the dog images and calculates each output value of neurons and then activate 5 neurons as a result. So we should be able to generate the next input that increase the inactivated neurons, such as the first neuron at the second layer in highlighted in green. So to do so, we calculate the gradient of the selected neurons and added them to new input for changing the selected neuron status from inactivate to activate. So let me explain the simplified workflow of white box testing method of DNNs. So the workflow consists of 3 steps. So it first select the neurons to activate. So in this example, let's assume that the first and the fourth neurons at the second layers are selected. Second, it calculates the gradient of the selected neurons. And the third step is to add their gradient to the original input in direction of the increasing their output values. Again, DNNs takes on new mutated inputs and repeat above the 3 steps for maximizing the neuron coverages. So in white box testing, answering the following question is key. Which neurons should we select first for the gradient calculation? That is so-called neuron selection strategy is a key component for effectiveness of the white box testing method. And recently, a diverse neuron selection heuristic have been proposed. And each strategy presented in each paper has its own criteria for selection of the neurons. Also, these research areas are still at early stages. Okay, let's sum up today's lectures. So ensuring that DNNs behaves as expected is a pressing issue in the recent research world. And as testing DNN is different from the testing traditional software, a diverse coverage metrics for DNNs have been presented in the literatures. So the goal of the DNN testing is to maximize a given coverage metric and find more adversarial inputs. And finally, to maximize given coverage metric, white box testing of DNN is to generate input by using the gradient of the selected neurons. Okay, this is end of this lecture. So see you next week. Bye.